For most of the last century, the only known object outside of Neptune was Pluto, a small planet with a diameter of only 2,300 kilometers, or 1,500 miles. Mysterious in appearance, strangely located at the edge of the solar system, Pluto was, until 2006, considered a planet in its own right, but it lost its rank as a planet to join the category of dwarf planets. Dear traveler, good morning. Today we are going to explore the confines of the solar system to discover the most incredible mysteries beyond Neptune. Before leaving for a new adventure, remember to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a nice trip. After the discovery of Pluto in 1930, scientists began to assume that it was not the most distant object in the solar system. At that time, no telescope had been able to detect objects that small at such a distant distance, but there was plenty of circumstantial evidence for the existence of dwarf planets, asteroids, meteors, meteorites, comets, and other celestial bodies at the edges of our solar system. Some scientists had their own ideas about what was lurking in that distant darkness. Most of these theories were based on the movement of comets. On August 30th, 1992, the first object in the Kuiper belt, the asteroid belt beyond Pluto, was discovered. It was given the name 1992 QB1. Since then, thousands of similar objects have been discovered in the Kuiper belt. Astronomers suggest that the hypothetical planet 9 could also be hiding in this area. It turns out that the limits of our solar system do not end here. There is another formation, and that is the Oort cloud. Scientists believe that the objects in the Kuiper belt and the Oort cloud are remnants of the formation of the solar system about 4.6 billion years ago. Let's go and discover this mysterious remote region of the solar system and the secrets it may hide. Since the 20th century, astronomers have been studying the inner region of our solar system. But even today, what lies at its periphery is still not known with precision. This mysterious area has become a source of exceptional discoveries for scientists. In recent decades, a number of space objects have been discovered there. As the technology for space exploration advanced, astronomers began to discover Transneptunian objects. Scientists were able to look beyond Neptune and discover a number of celestial bodies from the solar system in this previously unknown region. The Transneptunian objects were found to orbit our star at a distance of more than 4.5 billion kilometers. These objects form the Kuiper belt, and further away, the Oort cloud. The existence of objects far beyond Neptune was first proposed by the astronomer Frederick Leonard in 1930. According to him, Pluto is far from being the most distant object in the solar system, and it turned out that he was right. 13 years later, another astronomer, Kenneth Edgeworth, confirmed Leonard's words by advancing his hypothesis that at the edge of our system is a nebula filled with small bodies that never coalesced into a single planet. Today, we know that the solar system consists of the Sun and everything that orbits it, the planets and their satellites, the dwarf planets, the asteroids, the Kuiper belt objects, and the comets and the Oort cloud. The dimensions of the solar system are defined in terms of distance from the Sun to the Earth, called astronomical unit. One astronomical unit is equal to 150 million kilometers, or 93 million miles. One of the most distant known objects orbiting the Sun is the dwarf planet Eris, discovered in July 2005. Eris is located at a distance of about 97 astronomical units from the Sun. But at the edge of the solar system, at a distance of 90 astronomical units, there is another planetoid called Sedna, whose farthest orbit will be about 900 astronomical units. However, it is the long-period comets that travel the longest way around the Sun. These comets have extremely eccentric orbits and can reach orbital distances of 50,000 astronomical units and more. These comets originate from the Oort cloud, a huge spherical region composed of several billion comets. The Kuiper belt is often referred to as the edge of the solar system. This disk extends at a distance of 30 to 50 astronomical units from the Sun. Its existence has been reliably confirmed not so long ago. The Kuiper belt was named after the astronomer Gerard Kuiper, who predicted its existence in 1951. This hypothesis has been developed for quite some time. Many astronomers and astrophysicists have worked on it, trying to prove that the belt exists, or to disprove it. The hypothesis was gradually transferred to the category of theories and was not fully proven until 1988, thanks to a research paper by astronomer Julio Angel Fernandez, on the basis of which several Canadian scientists made calculations and confirmed the existence of a comet belt beyond Neptune. It was Fernandez who named this group the Kuiper belt in his paper, and the name quickly caught on. The first images of objects in this belt appeared in 1992, when astronomers discovered a reddish spot at a distance of 42 astronomical units from the Sun, the first recorded object of the Kuiper belt, also known as a Transneptunian object. Currently, more than 1,000 such objects have been discovered, larger than 200 kilometers or 125 miles, located well beyond the orbits of Neptune and Pluto. According to modern estimates, there are as many as 35,000 objects larger than 100 kilometers or 60 miles in diameter in the Kuiper belt, and the total number of bodies, according to experts, is estimated to be several billion. Therefore, the Kuiper belt has a total mass hundreds of times greater than the asteroid belt between the orbits of Mars and Jupiter. The Kuiper belt is essentially similar to the asteroid belt between Mars and Jupiter, but it is much larger and more massive than the latter. The Kuiper belt is actively studied today because its objects may be remnants of the early accretion phases of the solar system, older than any of the planets. Short-period comets can also be born there, in the same way that long-period comets are born in the Oort cloud. The Kuiper belt contains mainly small bodies left over from the formation of the solar system and several dwarf planets, including Pluto, which was demoted to this category from the ordinary planets in 2006. It is assumed that most Kuiper belt objects are composed of ice with small impurities of organic matter, i.e. close to cometary matter. In addition to the usual cometary nuclei of the Kuiper belt, objects have been found with a clear red color on their surface. The red color is considered a sign of the presence of molecules containing carbon and oxygen, organic compounds. Would comets have brought to Earth the raw materials for the origin of life? Scientists believe that the Kuiper belt is not eternal. The belt is made up of many objects that constantly collide, turning into dust. In a few 100 million years, the Kuiper belt will be a distant memory. The term dwarf planet officially appeared in 2006, when planets the size of Pluto and larger were discovered outside the orbit of Neptune. Since then, many bodies in the solar system have been called dwarf planets. The concept has caused much controversy, particularly regarding the status and nature of Pluto. The dwarf planets currently recognized by the International Astronomical Union include Pluto, Eris, Makémaké, Hauméa, and Ceres, the latter being located in the asteroid belt between Mars and Jupiter. These celestial bodies are called dwarf planets because they orbit the Sun with enough mass to become almost spherical. But unlike ordinary planets, they cannot clear their orbit of other objects. Indeed, for a body to acquire a spherical shape, it must have enough mass to oppose its own gravity. The internal pressure then forms the surface layer, providing the plasticity that fills the elevations and depressions. This does not happen with asteroids. Generally, these dwarf planets are made of layers of ice around a rocky core. They orbit in the Kuiper belt, a region beyond Neptune containing thousands of small frozen bodies belonging to a family of dwarf planets called Plutoids. The International Astronomical Union has determined that among Transneptunian objects, only those with a diameter of 838 kilometers or more become dwarfed. At present, the International Astronomical Union recognizes the existence of 5 dwarf planets, and about 200 await confirmation, and the total number is capable of exceeding 1,000. Potential dwarf planets include Orcus, 2002 MS4, Quaoar, Gong, and Sedna. Pluto is the second largest dwarf planet in the solar system after Eris. Originally classified as the 9th planet in the solar system, it is now considered a dwarf planet in the Kuiper belt. Like most Kuiper belt objects, Pluto is composed primarily of rock and ice and is relatively small. 5 times the mass of the Moon and 3 times its volume. Pluto's orbit has a large eccentricity and a large inclination to the plane of the ecliptic. Because of the eccentricity of Pluto's orbit, it approaches the Sun at a distance of 29.6 astronomical units. The Plutonian system includes 6 celestial bodies linked by gravity: Pluto and Charon, which are the 2 main bodies, and 4 moons of much smaller sizes: Styx, Nix, Kerberos, and Hydra. Pluto and its moon Charon form a binary system, and its barycenter is located outside Pluto. This feature is due to the ratio of the masses of the 2 bodies, which is quite large. The mass of Charon is worth about 12% that of Pluto. The composition of Pluto is represented by water ice, where there are 3 times more water than in the oceans of the Earth. The surface is covered by a crust of ice. There are visible ridges, light and dark areas, and a chain of craters. With a mass of 1,022 kilograms, or more than 1,022 pounds, which is about 0.2% of the mass of the Earth, Pluto occupies the 2nd position in terms of massiveness among the dwarf planets. Its atmosphere is a thin layer of nitrogen, methane, and carbon monoxide that evaporates from the surface ice. Thermodynamic considerations dictate the following composition of this atmosphere: 99% nitrogen, slightly less than 1% carbon monoxide, and 0.1% methane. As Pluto moves away from the Sun, its atmosphere gradually freezes and settles on the surface. As Pluto approaches the Sun, the temperature near its surface causes the ice to sublimate and turn into gas. This creates an anti-Earth effect. Like sweat that cools the body by evaporating from the surface of the skin, sublimation has a cooling effect on the surface of Pluto. Scientists have recently calculated that Pluto's surface temperature is about minus 230 degrees Celsius, or less than minus 382 degrees Fahrenheit. Pluto's orbit is highly inclined to the ecliptic, more than 17 degrees, and highly eccentric. It is very different from the orbits of the other planets in the solar system, which are almost circular and make a small angle with the ecliptic plane. The average distance of Pluto to the Sun is 39 astronomical units, but because of the great eccentricity of the orbit, this distance varies from 29 to 49 astronomical units. Sunlight takes about 5 hours to reach Pluto, the same time it takes for radio waves to travel from Earth to a spacecraft near Pluto. The dwarf planet Pluto has 5 moons. The largest and closest is Charon. It was found in 1978 by James Christie, who was looking at old photographs. The other moons are hidden behind: Styx, Nix, Kerberos, and Hydra. Charon, Styx, and Kerberos have the necessary mass to form spheroids, but Nix and Hydra seem elongated. In 2007, water crystals and ammonia hydrates were observed on Charon. This suggests that Pluto has active cryogeysers and an ocean. Satellites could have formed due to the impact of Pluto and a large body at the very beginning of the solar system's origin. At the beginning of the 20th century, scientists were looking for Planet X, now called Planet 9, which was responsible for the irregularities that still remained in the motion of Uranus. As a result, on March 13, 1930, Pluto was discovered by the American astronomer Clyde Tombaugh. Later it turned out that it was too small to fit the 9th planet theory, which would affect Uranus. The deviations of the orbit of Uranus has since received a different explanation. In fact, it is the mass of Neptune that has been wrongly determined. Since 1992, many icy objects have been discovered outside the orbit of Neptune, among them Quaoar, Sedna, and especially Eris, which is 27% more massive than Pluto. It has become clear to astronomers that Pluto is just a very large object in the Kuiper belt. On August 24, 2006, scientists at the International Astronomical Union removed Pluto from its planetary status, transferring it to the group of dwarf planets. Located beyond the orbit of Pluto, Eris is considered the largest dwarf planet in the solar system and the largest Transneptunian object in the Kuiper belt. It is so large that some call it the 10th planet. The discovery of the dwarf planet Eris, officially confirmed in 2005, was an important moment because it is larger than Pluto. It is the one that prompted the revision of the definition of the concept of planet. At the time of the discovery, scientists thought they were observing the 10th planet because it was a celestial body in the Kuiper belt that exceeded Pluto in size. Some agreed, but there were those who began to argue about the nature of the object. At that time, the definition itself had no clear criteria. The International Astronomical Union had to intervene in 2006 and present new criteria for classification. It turned out that some objects, including Pluto, do not meet the last requirement. Therefore, they proposed a new category, the dwarf planets. The diameter of Eris is about 2,400 kilometers or 5,300 miles, or 6% larger than the diameter of Pluto. Its mass has been determined from its moon, the tiny Dysnomia, which has a period of revolution of 16 days. Eris revolves around the Sun in 558 years. Its maximum distance is 97 astronomical units, and its minimum distance is 37 astronomical units. The orbit is extremely eccentric, but does not approach Neptune, so it is not influenced by the planet. Eris is bright and can be seen even with a small telescope. The presence of radioactive decay suggests a possible internal ocean in a liquid state. It has been shown the presence of methane ice, and the surface layer may resemble samples from Pluto. At its surface, the temperature oscillates between -243 and -217 degrees Celsius, that is to say, up to -405 degrees Fahrenheit. Initially designated 2005 FY9, Makémaké is the third largest of the dwarf planets, which was discovered on May 31, 2005, by the same team of Mike Brown at the California Institute of Technology by the Spitzer Space Telescope. This Transneptunian object still remains a mystery. The data showed that the diameter of Makémaké is 1,480 kilometers, or 920 miles. Its mass is 4 times 1,021 kilograms, or almost 1,022 pounds. Thanks to this, it is in third position in size among Transneptunian objects. The eccentricity is 0.159, so Makémaké approaches the Sun at a distance of 5.76 billion kilometers, or at the closest, 3.1 billion miles, and moves away from it until it reaches 7.94 billion kilometers, or more than 4.3 billion miles. It takes 309 years to orbit the Sun, and 7.77 hours to rotate its axis. Makémaké's orbit is located far from Neptune, so this object is free from the influence of this icy giant. The average density of 1.4 to 3.2 grams per cubic centimeter indicates that the celestial body contains a stone core and an ice crust. The ice is represented by frozen methane and ethane. The Herschel and Galileo telescopes have shown that the surface layer is very bright. The color of the dwarf planet Makémaké appears red, which means that it has a high level of tholins on the ice layer. In addition, it does not have a remarkable atmosphere, but methane is able to ensure a transitional atmosphere. Indeed, when a dwarf planet approaches the Sun, the sublimation of nitrogen and other ices occurs, forming a thin atmospheric layer. This would explain the depletion of nitrogen. Hauméa differs from other planets, not only by its elongation, but also by its high density and albedo. It does not have a spherical shape, but rather an ellipsoid. First named 2003 EL6, Hauméa is about the same size as Makémaké, which makes it one of the best-known Transneptunian objects of the Kuiper belt. It is extremely difficult to determine the parameters, density, and mass of this dwarf planet. It is a bright and large object, which makes it possible to calculate the albedo, but due to the rapid rotation, it is difficult to calculate its actual size. Because of its high reflectivity, it is the third brightest object in the Kuiper belt after Pluto and Makémaké. It is so bright that it can sometimes even be seen by powerful amateur telescopes, although its mass is only 32% of Pluto's mass. Estimates give a diameter of 1,632 kilometers, a mass corresponding to 1/3 of Pluto, Hauméa's massiveness is sufficient to reach hydrostatic equilibrium, that is, to allow it to have the shape of a sphere. The elongation of its shape is created due to the rapid rotation. The minimum distance between the Sun and Hauméa is 5.23 billion kilometers, or 3.1 billion miles, and the maximum distance is 7.7 billion kilometers, or 4.8 billion miles. It completes one revolution in 284 days with an orbital inclination of 28 degrees and makes one revolution on itself in 3.9 hours. Its density is between 2.6 and 3.3 grams per cubic centimeter, which converges with our Moon. In this case, Hauméa may consist of silicate minerals such as olivine and pyroxene. We can assume that most of the mass is made of rock with a thin crust of ice. It is possible that the mantle was much thicker in the past, but that it was worn away by numerous impacts. On one of these faces, a large dark red area has been noticed. This may be the scar of an ancient impact that left traces of minerals and organic compounds. Transneptunian objects are celestial bodies orbiting the Sun on an orbit greater than that of Neptune. All are located in the Kuiper belt. Pluto was the first body discovered in this belt in 1930. In 2012, the Transneptunian objects of the solar system already counted 1,400 celestial bodies, and in 2021, about 3,000. The diameter of the 9 largest of them exceeds 800 kilometers, or more than 500 miles in diameter. These are the dwarf planets Pluto, Eris, Makémaké, and Hauméa, as well as the objects Sedna, Quaoar, Orcus, Salacie, Varuna, and Ixion, which have not yet had the official status of dwarf planets. Generally speaking, the objects of the Kuiper belt are divided into 3 categories. First, the classical objects which have approximated circular orbits with a slight inclination, not associated with the motion of planets. The most famous dwarf planets are mainly among them, like Pluto, Eris, Hauméa, and Makémaké. Then, the resonant objects that form an orbital resonance with Neptune. The objects with a 2 to 3 resonance are called Plutinos, named after their brightest representative, Pluto, which means that they make 2 orbits around the Sun, while Neptune makes 3, among which Orcus and Ixion. Finally, the scattered objects that have a large orbital eccentricity and can be several hundred astronomical units from the Sun at aphelion. It is thought that long ago, these objects got too close to Neptune, whose gravitational influence stretched their orbits. An excellent example of this group is Sedna. Today, Sedna is considered the most distant object in the Kuiper belt. The size and distance of Sedna from the Sun do not allow scientists to say with precision to which class this cosmic body belongs. Various hypotheses are nevertheless advanced. But astronomers already know the color, composition, and even the detailed orbital characteristics of the planet. Namely, Sedna's orbital period is 10,500 years, and its diameter is a little more than a quarter of that of Pluto. Its orbit is elongated, and at its furthest point, it is 900 astronomical units from the Sun. For comparison, the radius of Pluto's orbit is 38 astronomical units. Sedna's size is quite large. Its diameter fluctuates around 1,000 kilometers or 620 miles, making it the 6th largest among Transneptunian objects. Sedna's composition was calculated using a series of spectrographic studies from 3 orbiting telescopes. It is similar to the compositions of other Transneptunian planets, comets, and gas giant satellites. Signs of water ice were found, as well as ices of frozen organic matter. Astrophysicists estimate the final density of Sedna at 2 grams per cubic centimeter, comparable to the density of ordinary kitchen salt. Sedna represents the most attractive object for astronomers. Indeed, the mystery of the distance of its orbit may reveal the secrets of the history of the formation of the solar system, now built mainly on theories. In addition, Sedna itself is a true archaeological monument, because due to its isolation from other objects, it has preserved the properties inherent to the original material of our solar system. Quaoar is a celestial body discovered in 2002 by scientists from the Palomar Observatory in California, and named after the deity of the Tonga Indian people. Its diameter is 1,260 kilometers, or almost 780 miles. This is about 1/10 the diameter of the Earth, 1/3 the diameter of the Moon, and about half the diameter of Pluto. Quaoar orbits 42 astronomical units from the Sun, with a period of revolution of 288 years. It has an almost circular orbit and moderately inclined. Its angle to the ecliptic is about 8 degrees. Quaoar is classified as a classical Transneptunian object. The orbit, however, is unusual for large classical objects, which usually follow more eccentric and inclined orbits. Although Orcus has not yet been officially classified as a dwarf planet by the International Astronomical Union, many astronomers agree that it meets all the requirements and will be in the future. Discovered in 2004, Orcus turned out to be a large Transneptunian object with about 958 kilometers in diameter. That is almost 600 miles in diameter. In addition, Orcus appears to have an albedo of about 21% to 25%, which is typical of Transneptunian objects approaching the diameter range of over 1,000 kilometers, or over 620 miles. In terms of mass, the Orcus system is estimated to have about 3.8% of the mass of the dwarf planet Eris. Like Pluto, Orcus has a very long orbital period, taking 245 years to complete a single rotation around the Sun. It is also in 2 to 3 orbital resonance with Neptune, and lies above the ecliptic during perihelion. Moreover, its orbit has an inclination and eccentricity similar to those of Pluto. Orcus orbits the Sun at a distance of 30 astronomical units at perihelion and 48 astronomical units at aphelion. However, Pluto and Orcus are oriented differently. On the one hand, Orcus is at aphelion when Pluto is at perihelion, and vice versa, and the aphelion of Orcus' orbit points almost in the opposite direction of Pluto's. That is why Orcus is often called anti-Pluto. Salacie is a Transneptunian object located in the Kuiper belt, classified as a separate object. It orbits the Sun in an elongated orbit, at an average distance slightly greater than the semi-major axis of Pluto's orbit. At the time of its discovery, on September 22, 2004, astronomer Michael Brown calculated that Salacie is most likely a dwarf planet. However, many astronomers argue that objects such as Salacie in the diameter range of 400 to 1,000 kilometers, or 250 to 620 miles, with an albedo of less than 0.2 and a density of 1.2 grams per cubic centimeter or less are probably not dwarf planets. Many astronomers believe that Varuna is shaped like a rugby ball about 900 kilometers in diameter, about 1/15 the diameter of the Earth, 1/4 the diameter of the Moon, or 1/3 the size of Pluto. Varuna has a nearly circular orbit, orbiting at about 43 astronomical units from the Sun, making a revolution in 283 years. It takes about 3 hours to complete one rotation around its axis. The orbits of Varuna and Pluto have the same inclination and are oriented in the same way. Varuna is not subject to significant disturbances from Neptune. This Transneptunian object could very well be a dwarf planet, although astronomers have not officially classified it as such. It was discovered on May 22, 2001, and is named after Ixion, a figure from Greek mythology. It is one of the largest Plutinos, i.e., a Transneptunian object with an orbit similar to that of Pluto. Like Pluto, Ixion is in 2 to 3 orbital resonance with Neptune. The latest spectroscopic results indicate that the surface of Ixion is composed of a mixture of black carbon and tholline, an organic substance more or less nitrogenous, of red-brown color, sometimes purplish, and of poorly known structure. The Kuiper belt begins slightly beyond the orbit of Neptune, at 30 astronomical units from the Sun, and ends at about 50 astronomical units from the Sun. But there is one thing about the Kuiper belt that is a huge mystery. Once we get to 50 astronomical units, the belt stops. It ends suddenly, something astronomers call the Kuiper cliff. But then why this sudden change of environment? The mystery can be answered through different hypotheses. It could be that the belt continues, but the objects become so small that we can't see them. But this idea does not fit with what we know about the formation of the solar system. Instead, because of the complex interactions of the orbits of the outer planets, we expect the objects to start growing again at this distance. A more exciting idea is that the objects may have been attracted by the gravitational pull of an as yet unknown planet. Such a planet, which would be the 9th planet in the solar system, could be the size of Earth or Mars. The possible existence of a Planet 9 at a very great distance from the Sun thus brings up the question of the number of planets in our system. It is quite possible that other planets are located at large distances from our star, so that their perturbations on the surrounding objects have not yet been noticed. Unfortunately, it is difficult to see anything from that far away, so the mystery is not over yet. Beyond the Kuiper belt is another formation, called the Oort cloud. The idea of the existence of such a cloud was first put forward by the Estonian astronomer Ernst Eppik in 1932, then theoretically developed by the Dutch astrophysicist Jan Oort in the 1950s, after whom the cloud was named. It has been suggested that comets originate from an extended spherical envelope of icy bodies at the periphery of the solar system. This huge swarm of objects is now called the Oort cloud. It extends in a sphere with a radius of 5,000 to 100,000 astronomical units. The Oort cloud is a hypothetical region located halfway between the Sun and the heliopause, the limit where the solar wind of our Sun is stopped by the interstellar medium. Astronomers believe that the existence of the Oort cloud explains why some comets have extremely long orbital periods. A fragment of dust and ice can remain in the Oort cloud for thousands of years, Some nearby stars pass close enough to the solar system that their gravitational force pushes an object out of the Oort cloud into orbit around the Sun. The Oort cloud is the biggest mystery in the solar system. We have never seen it. It is a hypothetical region in space. Unlike the Kuiper belt, we can observe the large Transneptunian objects, and we know where it is, but the Oort cloud is very enigmatic. The Oort cloud is expected to be more than 50,000 astronomical units from the Sun, that is beyond a light year, or about 25% of the way to our nearest stellar neighbor, Proxima Centauri. The Oort cloud is therefore very far away. The confines of the Oort cloud are roughly at the edge of the solar system, and at this distance, the billions of objects in the Oort cloud are very loosely gravitationally bound to the Sun. They can therefore be strongly influenced by the passage of other nearby stars. It is thought that the disruption of the Oort cloud can cause icy bodies to periodically fall inward, creating long-period comets, such as Halley's Comet. In fact, this is the only reason astronomers believe the Oort cloud exists. It is the source of long-period icy comets that have very eccentric orbits, emanating from regions outside the ecliptic plane. This also suggests that the cloud surrounds the solar system and is not confined to a belt around the ecliptic. Thus, the Oort cloud appears to be out there, but we cannot observe it directly. Being so far away, with so little light, we simply don't have the technology to see it. This means that at the moment, we have no way of proving that it exists, or if it does, how big it is. This is the biggest mystery in the farthest region of our solar system. In 1950, the Dutch cosmogonist Jan Oort, after analyzing the distribution of the orbits of the then-known comets, suggested that long-period comets originate in a region at the edge of the solar system, 20,000 to 200,000 astronomical units away. If originally, in 1950, Oort assumed that these bodies were the result of the explosion of a hypothetical planet, by 1951, his hypothesis changed to come closer to modern conclusions. Most likely, this cloud formed from an original protoplanetary disk of dense gas, which in turn appeared near the Sun, still very young, at the beginning of the formation of our system. This cloud could therefore be more than 4.5 billion years old now. In fact, the Oort cloud is a continuation of the Kuiper belt. The objects could have merged closer to the Sun, but due to the gravitational attraction with the gas giants, they were ejected to a very large distance. Indeed, the process of evolution of the giant planets, especially Jupiter and Saturn, when they reach a sufficiently large mass, create gravitational disturbances that become so strong that they begin to massively eject planetesimals from the closest areas of their orbits. This cloud, which is made up of millions of these icy bodies, was later called the Oort cloud. It is a giant reservoir in which cometary bodies are found, and from which, under the influence of stars approaching the Sun or giant gas dust clouds, change their orbit to fall into the inner regions of our solar system. A study by NASA scientists has shown that the enormous volume of these objects is the result of an exchange between the Sun and neighboring stars. Computer models show that galactic and stellar tides modify cometary orbits, making them more circular. This may be the reason why the Oort cloud takes the shape of a sphere. The simulations also confirm that the creation of the outer cloud is consistent with the idea that the Sun appeared in a cluster of 200 to 400 stars. The composition of the Oort cloud includes two parts: a spherical outer cloud, 20,000 to 50,000 astronomical units, and an inner disk cloud, 2,000 to 20,000 astronomical units. The outer one is inhabited by trillions of icy bodies with a diameter of 1 kilometer, i.e. less than 1 mile, and billions of 20 kilometers, i.e. more than 12 miles. They have no information on the total weight, but if the Halley Comet is a typical body, then calculations lead to a figure equivalent to the mass of 5 Earths. Sometimes passing stars disrupt the orbit of one of the bodies, causing it to move through the inner solar system like a long-period comet. These comets have a very wide and elongated orbit, and as a rule, are observed only once. An example of a long-period comet is Halley and Swift-Tuttle. Most comets are filled with water, ethane, ammonia, methane, hydrogen cyanide, and carbon monoxide. 1 to 2% may be made up of asteroidal objects. On the other hand, short-period comets with an orbital period of less than 200 years move in the plane of the planets and come to us from the Kuiper belt. The Oort cloud is thought to have the highest density in the plane of the ecliptic. About 1/6 of all the objects that make up the Oort cloud are found here. The temperature here is no higher than -269 degrees Celsius, or -452 degrees Fahrenheit, which is close to absolute zero. The space behind the Oort cloud no longer belongs to the solar system. In the past, comets were considered to be stars with tails. Comets can be visible for weeks in the night sky. Aristotle thought that comets were glowing vapors in the atmosphere. The Danish astronomer Tycho Brahe realized that these celestial bodies are further away than the moon and come from deep space. Edmund Halley discovered that the comet of 1682 had the same orbit as the comets of 1531 and 1607. It was therefore the same object. Galileo predicted the return of this comet in 1758. Comets move around the Sun on elliptical orbits very elongated. The periods are very variable, from a few years to several thousand years. Most likely, long-period comets travel from the Oort cloud, located at the outer limits of the solar system, in which millions of cometary nuclei circulate. In general, comets orbit the Sun in two distinct groups, in the Kuiper belt and in the Oort cloud. Most comets with orbital periods of less than 500 years come from the Kuiper belt. These comets are small bodies of the solar system, formed by porous pieces of ice, mixed with dust particles of several kilometers and miles in diameter, without determined shape. Their composition has remained identical since the birth of the solar system, which is priceless for science. Circling the Sun in elongated orbits and having the appearance of nebulous objects, comets move in distant orbits, where they remain invisible, and when they approach the Sun, the ice begins to melt under the influence of solar heat, evaporating and volatilizing into interplanetary space. As a result, many comets passing close to the Sun take on a very unusual appearance. The comet develops a tail of bluish gas and a tail of yellowish dust. The tail, even very thin, can be spectacular. The dust spreads along the orbit. If a comet enters the Earth's atmosphere, It is called a meteor. Most comets that appear periodically in the vicinity of the Sun are rather faint objects. The exception is Halley's Comet, which appears before us as a very bright object almost every time it returns to the Sun. In fact, the brightest and most spectacular comets appear in the sky unexpectedly, many of them perhaps approaching the Sun for the first time. In rare cases, especially if the comet gets too close to the Sun, it may break up into pieces, which are then observed as separate bodies. All comets have a hazy gaseous envelope, the hair or coma, which together with a nucleus forms the head of a comet. Even if the comet is close to the Sun, its head seems to be nothing more than a hazy point. The most remarkable detail of most comets is the tail. It is brightest when the comet is near the perihelion of its orbit. Here, the heat flux from the Sun is particularly important, under the influence of which gases and dust escape from the comet into space. Some comets have two tails. One is curved, made of dust particles, the other is straight, gaseous, elongated in a direction exactly opposite to the Sun. The length of the tails of comets can reach tens and hundreds of millions of kilometers, so comets have been observed whose tails extended over nearly half the sky. It is assumed that the dust lost by comets falling into interplanetary space gives rise to meteoroids, which later, colliding with the Earth's atmosphere at high speed, are found in the form of meteors. The dust particles from the tails of comets also reconstitute interplanetary dust clouds, which by scattering the Sun's rays, give rise to a phenomenon called zodiacal light. The nucleus of a comet is sometimes visible inside its envelope, as a bright star-shaped object in which it is not possible to distinguish details, even with the largest telescopes. Comet nuclei have been studied in detail by spacecraft that have approached comets. In 2005, NASA's Deep Impact spacecraft collided with Comet Tempel 1 and sent back images of its surface. The masses of comets are very small, about 1 billion times smaller than the mass of our Earth, and the density of matter in their tails is almost zero. Therefore, they do not affect the planets of the solar system. The most famous of these is Halley's Comet, which returns to the Sun every 76 years. The last time it approached the Sun was in 1986. History notes the fear of our ancestors before these celestial wanderers, and very often we can find in ancient chronicles references to the appearance of bright comets in the sky, and the link of these phenomena with terrestrial incidents such as fires, wars, and even the death of individuals. A good and fairly well-studied example of such a collision was the collision of debris from comet Shoemaker-Levy 9 with Jupiter. In July 1994, fragments of this comet bombarded Jupiter's dense atmosphere at speeds of up to 210,000 kilometers per hour, or more than 130,000 miles per hour. During the impact, the incredible kinetic energy of the fragments was released in powerful explosions, some of which turned into fireballs larger than the Earth. As a training exercise in case an asteroid ever threatens to hit Earth, NASA's DART probe collided head-on with the Dimorphos asteroid on September 27, 2022. The impact was just enough to push the asteroid into a slightly closer orbit around its companion space rock. This successful mission was a first for NASA as part of a planetary defense program to develop solutions to deflect asteroids should they threaten Earth. It is not quite correct to speak of the boundaries of the solar system in our terrestrial geographical sense. In space, all limits are conditional. They are determined with the help of many data recorded by instruments. Everyone knows that the sun is a source of light and heat, but in addition to that, the sun constantly emits a huge stream of plasma. This is called the solar wind. To answer the question of where exactly the solar system ends, you need to understand where the solar wind flies and where solar gravity stops dominating. The particle stream travels at a speed of about 1.5 million kilometers per hour, or more than 1 million miles per hour, creating a kind of analog of the atmosphere that exists on some planets. This formation is called heliosphere. Thus, the area that is under the constant influence of the solar wind is called the heliosphere. The limit of the heliosphere, called the heliopause, is located at a distance of about 100 astronomical units from the Sun. The question of where exactly the solar system ends and interstellar space begins does not currently have a clear answer. When determining the conditional limits of the solar system, it is necessary to take into account two main factors: the distance where the action of the solar wind ends, and the distance over which the star's gravity extends. At a distance of 60 to 70 astronomical units from the Sun, the solar wind begins to slow down rapidly due to interaction with interstellar gas, and at the heliopause, the solar plasma flow is completely balanced by the pressure of the interstellar gas. However, the Sun's gravity dominates at much greater distances. Some scientists believe that the Hill sphere, which is a sphere dominated by the gravitational influence of the body, extends to 125,000 astronomical units for the Sun. Therefore, it is this distance that can be called a full-fledged edge of the solar system. The famous American spacecraft Voyager 1 and Voyager 2 left Earth in 1977 to study the giant planets. Each spacecraft is equipped with instruments to measure the magnetic fields and particles it passes through. Since then, both probes have traced their way to interstellar space and thus to the heliosphere. However, trying to understand the whole heliosphere from two probes, Voyager 1 and 2, is like trying to understand the weather in the whole Pacific Ocean with two weather stations. Thus, to better study the heliosphere, the two probes collaborate with the Interstellar Frontier Explorer. The latter is a satellite of the size of a suitcase of 80 kilograms or 175 pounds, launched by NASA in 2008. Since then, it has been orbiting the Earth, equipped with telescopes that observe the outer limits of the heliosphere. The IBEX satellite captures and analyzes a class of particles called energetically neutral atoms, or ENAs, that cross its path. These atoms form where the interstellar medium and the solar wind collide. Some atoms return to the center of the solar system and the IBEX satellite. Therefore, by collecting many of these individual atoms, it is possible to create a picture of our heliosphere from the inside. In 2012, Voyager 1 went beyond the heliosphere, and in December 2018, the probe Voyager 2 did the same. But despite this, the devices are still sending signals to Earth. They found that cosmic rays outside the heliopause are about 3 times more intense than inside the heliosphere. In addition to the Voyagers 1 and 2 missions, other devices are also operating on the outskirts of the solar system, such as Pioneer 10, Pioneer 11, and New Horizons. These vehicles will also eventually leave the heliosphere and enter interstellar space, as did Voyagers 1 and 2. In 2006, NASA sent the probe New Horizons, whose main objective is the study of the dwarf planet Pluto and its moons. It arrived in 2015, showing for the first time the surface of the former 9th planet. Now it is heading to the end of the Kuiper belt to examine its objects. In space missions, we still have not reached the Oort cloud, which is even further. Voyager 1 is the farthest probe from Earth at 23.3 billion kilometers, or almost 15 billion miles from Earth. Given the current acceleration, it would take another 300 years for the spacecraft, now in interstellar space, to reach the Oort cloud, and more than 30,000 years to get out completely. It will be followed by Pioneer 10 and 11, Voyager 2, and New Horizons. But in view of the little energy remaining in the probes, maximum a decade, they will not be able to transmit data when they reach it. Thus, the main difficulty of the study is the enormous distance. The time that the probe reaches, centuries will have passed. For now, we can only look at incoming comets. An interesting fact is that after several tens of thousands of years, the probes will encounter other stars. For example, the probes Voyager 1 and Pioneer 11 will encounter the star Proxima Centauri, and Pioneer 10 and Voyager 2 will encounter the small red dwarf Ross 248. In 2025, NASA will launch the Interstellar Mapping and Acceleration Probe, or IMAP. The cameras capturing energetically neutral atoms on IMAP have a higher resolution and are more sensitive than the cameras on IBEX. When defining the limits of the solar system, it is necessary to indicate what can be considered as its limit. To date, 3 hypotheses are considered. According to the first hypothesis, the radius of the solar system is considered until the end of the aphelion of the most distant planet, which is Neptune. In this case, the radius of the whole system will be 4,545 million kilometers. As for the second hypothesis, scientists consider that the radius of the solar system is defined at the end of the most distant observed object, which is currently Sedna. In this case, the radius of the entire solar system would be 143 billion kilometers, or about 89 billion miles. To simplify the calculations and understand the size of the solar system, the measurements must be taken not in kilometers or miles, but in astronomical units, knowing that 1 astronomical unit equals 150 million kilometers, or 93 million miles, that is to say, the distance of Earth to Sun. In this case, the radius of the orbit of Sedna is 955 astronomical units. Finally, according to the third hypothesis, the radius of the solar system is considered until the edge of the heliosphere. In this case, the radius of the whole system will be 90 astronomical units. Thanks to new data, specialists have created a 3D map of the solar system after 13 years of work. The measurement of the 3D map was collected by a research satellite called Interstellar Boundary Explorer, which was launched in 2008. The research satellite behaved like a bat in a cave. Only instead of sonar or the voice of an animal, the solar wind was used. During the entire cycle of solar activity, from 2009 to 2019, the device measured the flow of particles that swept it towards interstellar space. And at the same time, it was trying to catch the atoms that were returning to the interior of the solar system. Well beyond the orbit of Neptune, about 60 astronomical units, the solar wind collides with the interstellar plasma. This interaction not only slows down the particles emitted by the Sun, but also generates a stable stream of high-energy neutral atoms. It is rather weak, but perceptible, and above all, it has a strictly unique nature. The journey of the solar wind from the star to the heliospheric field takes from 2 to 6 years. By carefully measuring solar activity and the flow of high-energy neutral atoms, scientists have compared these two multi-directional particle flows. As a result, it was possible, for the first time, to compile a three-dimensional map of the heliospheric boundary. Thus, the developed 3D map revealed even more data about the heliosphere. In particular, the shape of the inner layer, in which the Sun and planets are located, resembles a spherical layer. According to the scientists, it extends about 90 astronomical units in all directions. They also believe that the shape of the outer layer is much less symmetrical. In fact, in the direction in which the constantly moving Sun crosses space, colliding with the cosmic radiation, the outer heliosphere extends about 110 astronomical units. But in the opposite direction, it is much longer, at least 350 astronomical units. The lack of symmetry is due to the movement of the Sun along the Milky Way. According to scientists, there is a lot of plasma, or charged particles, in the interstellar medium, and the inner heliosphere, which is quite round, is a barrier to this plasma flow through it. This has the same effect as water flowing around a rock in a stream. There is some debate about the exact shape of the heliosphere. However, scientists agree that it has several layers. Let's look at the layers from the inside out. First, there is the layer called the terminal shock, which represents the deepest layer of the heliosphere, surrounding all the major planets in our solar system. Here, the solar wind from the Sun disperses at full speed, at more than 1,000,000 kilometers per hour, over billions of kilometers, defying the particles of the interstellar medium coming from all over the galaxy. The outer limit of this main layer is called the shock wave limit. Next, we find the helio gap, which exists outside the shock wave boundary. In this layer, the solar wind moves more slowly and deflects when it encounters the pressure of the interstellar medium outside. Then, the heliopause, which marks the clear and final plasma boundary between the Sun and the rest of the galaxy. In this layer, the magnetic fields of the solar and interstellar winds are pressed against each other, and the internal and external pressures are in equilibrium. Finally, there is the outer helio gap, which represents the region outside the heliopause that is still affected by the presence of the heliosphere. To learn more about the heliosphere, NASA plans to launch a new mission in 2025 called the Interstellar Mapping and Acceleration Probe. Scientists hope this will give them a better understanding of how solar winds and cosmic rays interact at the edges of the solar system. Our Sun is a star, like billions of others in the universe, some of which also have astrospheres. Our heliosphere is the only astrosphere we are actually in and can study closely.